Thank you, Juniata, for inviting me and giving the opportunity for me to share some of my research project and my research topic here. So I titled my presentation Algorithm Assisted Architectural Design with Python Packages. So and kind of a short introduction on my background. So I did my PhD back in Singapore with Future Cities Laboratory with the ETH Singapore Center. And I also did my postdoc with the Singapore MIT Alliance for Research and Technology and with National University of Singapore. And after that, I came to Princeton to continue my postdoc studies. So my research focus has always been on computational design with a focus on energy-related problems. So for my PhD, I look at the effect of considering engineering systems, especially air conditioning system, on the envelope and architectural design process in the early design stage, and how do you integrate all these considerations in the early design process. So what is an algorithm? Algorithms is essentially a well-defined step, a well-defined series of steps to achieve a certain objective, and usually they can be run computationally without the need for manual intervention. So when you are able to effectively use algorithms in design, the main aim is to reduce as much as possible manual work and be able to perform more creative tasks, such as reflection and discussion in a team, in the collaboration team. So essentially what Darren has presented previously, where if information can flow more smoothly, that you can actually spend more time discussing the clashes or the issues with some of the design solutions, instead of trying to make sure that every software talks to each other and spending time on trying to standardize and streamline that process. So that's the kind of the main objective of using algorithms in the design process. So some of the tasks that can be assisted by algorithms, Darren's presentation has shown some of them, but on a more kind of studio design based or student educational based context, some tasks that can be assisted are like GIS based site analysis, execution of simulation, evaluating a design solution, exploration. So if you can parameterize your design, you can generate multiple models and then evaluate them, and then eventually you can put the parametric model, the evaluations and so on into let's say a genetic algorithm or any search algorithms, and automatically generate like thousands of designs, and then you can explore the solutions generated and kind of fit back into your design process and understand your design problem. And there are many tools that you can use to do that. So I guess most of you might be familiar if you're from architecture, like Grasshopper, Dynamo, and so on. And then for maybe little students who are more advanced, who's familiar with programming and coding, you can look at Python and so on. So there's many programs out there that you can explore and use to kind of develop an algorithm-assisted design process. So for this presentation, I will present one project that I did with one of the lecturer in SP a few years ago, Tian Xiong, where we conducted a 2 weeks workshop, and I tested out some of the workflows that I designed for the students. So Py for Design is a Python library that I work on and I develop, where the main objective and aim is to be able to perform performance-based design design process and link multiple analysis software, different formats like IFC, CDGML, and so on, and make performance-based design process supported by digital tools as painless as possible. So that was kind of the objective when I started developing this Python library. So this is the project essentially that I applied this package into, and this was a 2 weeks workshop for architecture students to learn and execute algorithm-assisted design process. So I streamline a lot of the process, and I give them kind of like fixed interface for them to engage in such a design process. So the main idea is to expose them to what such a process can be. Instead of emphasizing on teaching them the tools, I'm hoping that within 2 weeks they know what such a design process can be, and then if they're interested and motivated, they can kind of go back and pick up useful tools to implement this on their own if possible. So that was kind of the objective. So in terms of that, so the design brief given to them was very simple. So I gave them a site like this, and there's some surrounding buildings, and a simple plot was given to them, and they were asked to design a high-rise tower using the algorithm design process, assisted design process that I have set up for them. So first of all, what should you design according to what objective? So two simple ones. So one is to maximize the FAR, or in Singapore we call it the plot ratio, right? So the amount of built-up area divided by the plot area will give you how well you utilize the site. So you want to build as much as possible, but at the same time, you want to make sure that what you build is able to have well-designed solar shading, but at the same time have some daylighting. So I invented the indicator called useful solar facade area index. So essentially the amount of solar irradiation that's received on the facade of the meshing have to be within a range between 245 to about 350. So that's like that's the sweet spot that you have enough daylighting going in to the interior, but it's not too hot that you overheat your building. So you have to satisfy this performance when you're doing your design. So what I did was with the Python design Python library, I set up a workflow for a 3-stage design process. So the first stage is what I call a concept exploration. So I asked the students to model a building meshing in SketchUp, because SketchUp is essentially because it's free, so there's no licensing issue and so on. And it's just a 2 weeks workshop, so the easiest 3D modeling software that I can find, and that's most accessible. So I asked them to model a building meshing, a meshing model, and then I tell them to model three different options manually. So you explore what is a good meshing that give you enough FAR, but at the same time is well shaded. And I give them a script. So this is kind of like an IDE development environment, integrated development environment. So they just have to specify the SketchUp file, the 3D model that's exported from SketchUp. And then this is the site model, which is what I give to them. And that's the weather file path for Singapore. So once you model your model in SketchUp, you export it to Collada or .dae, and then you specify in this script, and it will automatically generate the performance model on the right. So you can look at, and the indicator is given. So like, FAR treat, FAR like what is the build up area, and then how well are you performing in terms of solar related performance. So you can see like the H is performing better because there's certain shading area and so on. So this is the first stage. So you manually model it, you put it in, you kind of simulate, and then you kind of have a performance idea of your meshing. So the second stage, where I call it parametric exploration, I gave the students about seven morphological operators to parameterize the design. So what they need to do is they still model it in SketchUp, so they export the model, and then a script was given to them where you can specify, or do you want to twist your meshing? Do you want to taper your meshing? Do you want to slant it and bend it and so on? So you can specify it. True. So if you say it's true, it will do it. If you say it's false, it won't do it. So what is the value and so on? So you can combine all these morphological operators, and then you can very quickly generate a design alternative from a single, I call it concept model. So you can kind of parameterize a concept model, and you can generate kind of variations and alternative to it. And then again, you would put it in and run the performance. So this is all included in the script. So we will always run these two performance, and you can see as you change, how does this affect the performance. So you can quickly explore the various different variations of a single concept model. So that's essentially parameterizing your design. And then the last stage is instead of setting one single height value or one single taper or twist value, you kind of specify a range. I want to twist my tower between 0 to 90 degree at a 5-degree interval, right? So that would help you generate like a huge range of designs based on how you set up your inputs. And then once you do that, so this script here automatically put this scheme that you have defined into optimization algorithm, and it runs for overnight essentially, and it will generate like a few thousand or few hundred designs. So for the workshop, I tell the students to just generate like about 250 designs for each concept model. So once you've done the parametric design, you would choose one of the model to be used in the algorithm exploration stage. And then once you run your design, you run the algorithm overnight. So this is what you can see. So like this is 250 designs, and you can look at what we call the Pareto Fund. So a Pareto Fund is when you have more than 2 performance objectives. So here you can see there's 2 performance objectives. For example, Y can be the solar performance, and X can be the FAR. So you want to optimize both of them, right? So you want to maximize both. And you can see all the red dots. So each dot is a design options or design alternative generated by the optimization algorithms, and the red dots are what we call the Pareto Fund. So they are like the best designs, because if there's 2 performance, there's no one single best design, there's multiple best design, and you can they are on the Pareto Fund because they are non-dominated by any other design alternative. So what is dominated? So H is dominated by D because you can see that D performs better in terms of the solar, and FAR better than H. But the thing is, you can't say that let's say A and B, you can't say which one is better because B performs better than A in terms of solar, but A performs better than B in terms of FAR, right? So A and B is actually equal. You can't say which one is better than which, and that's what we call the Pareto Fund. And you can choose which one more. You can choose the design from the Pareto Fund to further develop into the next stage, to more detailed design. So that's kind of what I introduced to the student. So as a result, you can see this is one of the 250 designs that's generated by one of the students. And you can see those designs that's on the Pareto Fund, and those designs that, although it's not on the Pareto Fund, is still promising. So you can still look at all this and decide whether the performance is good enough. And if it's not good enough, but you still like it, right? So design is not just about performance; it's also about the design, your expression of your design. So if you choose something that you like but perform worse, so you can still refine it in your next detail stage to make sure that it can perform as well compared to the other options that you have given up. So this provides insights into how you should your insights into your next step in your design process, and give you a boundary of how well my design can be, if I have chosen other alternative. So in this diagram, or in this image, these are all the designs generated by in the workshop by all the students. So like 28 students attended the workshop. 27 out of 28 students completed the exercise. So completed the exercise defined by finishing all the 3 stages. So one student couldn't, get it to work for the 3rd stage. So she was only able to perform the 1st and 2nd stage design, and was unable to do the 3rd stage, due to some technical problems and installations and so on. Because in this workflow, you're connected to Radiance analysis software and some other geometry library. So that you have to make sure that it works well together. But collectively, about 5,000 designs were collectively explored by the students. And you can see all the students' design here, and those students who generated design that's on the Pareto Fund of all of the 5,000 design alternative. So you can see student 21, student ID 21, found a good concept, or found like a high performing design concept, and that's why most of her design are on the Pareto. So, and you can see other design meshing that is created to that kind of perform well. And then they were asked to submit all of their their models, 3D models, and their performance to me, so that I can kind of evaluate and understand what's happening and so on. So something really, well, it's not interesting, but it kind of just validates some of the ideas that we always say, that if you explore more design, you'll find better performing designs. That's kind of what we always tell students, but we never really have numbers or evidence to show that. So by looking at the 3 different stages where students were given the capability to explore design with better support from digital, with better digital support, we can see that as they explore more designs. So you can see in stage 1, on average, each student in stage 1 explore about 8 designs alternative. In stage 2, about 28, and in stage 3 176, because it's automated by the genetic algorithm. And in stage 2, because they were given the morphological operators, it's much easy to quickly vary their concept models. That more so like more of the Pareto Fund that was generated. So more of the designs on the Pareto Fund are generated during stage 3, where they are able to look for more designs using an algorithm, and they were able to find better performing designs using that. So kind of just prove that HO saying of, if you explore more, you will be able to find better performing design. So that's so there's some data to show that. And with that, I end my presentation here. And for anyone who's interested to look at the workflows, you can look at the papers that was published based on this workflow. And if you have any questions, you can feel free to kind of email me on any questions for this presentation. So thank you.
Thank you, Dr. Chen. I mean, I've always been amazed by what all this, Python, all this scripting can actually do, but I've never really got down to put my hands into it. Would like to learn a thing or two. Yeah.
Well,
so any questions from the floor? Yeah. Is it hard to learn, Dr. Chen, to acquire these skills?
I think so. For Python, I wouldn't say it's hard, but you definitely need to have background. Like you need to. There's a lot of effort required. So like, because it's still coding. So
okay.
But there's a lot of help, especially for Python online. So you will be able to find very good help online.
Right.
But essentially, it still takes a lot of time and effort. So that's kind of the drawback on that. But I mean, if students are able to learn Grasshopper on their own, I think they can learn Python on their own too, if there's a motivation and drive. So
yes.
Yeah.
So your contact is actually here in the
slide.
In your slides, right? Okay, so
Yes.
So feel free to contact Dr. Chen if you need any more, any help on this. I mean, maybe at this point, because they may have not gone through their design development yet as for the competition, so they may not have any questions as yet. So later, maybe it could be later on when they are in the midst of their project. It could be that way.
Yeah.
Okay, anything from anyone?
I was going to say I have a question. Curious to know anyway. It's always been one about, like, I see that sort of stuff at a maybe not only academic level, but I see you see show reels of people doing this sort of thing. I've yet to, or I don't think I'm yet to encounter it actively being used on projects. So I'm wondering, what is the barrier for architectural design practices and things, or larger, corporations? What do you think is the barrier to them using these sorts of tools?
Yeah, so I always thought it was a technical barrier, but okay, I can share one experience with you, and then that makes you realize it's more than a technical barrier. So I was invited to work in a competition with one of the architects in Singapore to try out such a design process. And what I realized was, so going in, I was very confident, like, oh, if I can, I'm quite good at doing this. So if they just, work with me, I will be able to kind of set this up and then help them run this. But what kind of hit me was that it's a more fundamental issue between design and computation. So I mean, in a lot of design practices, it's a lot of more intuitive moves. So in the design process, for example, they would look at the brief, draw some sketches, make some quick models, and then they reflect on it, and then it's a reaction between the brief, the solution, and then they would make changes again to the design. So it's a lot of a lot of fuzzy logic and a lot of unknowns as they design. And the thing is, when they consulted me and say, "Oh, I want to try some of this performance-based design process," one of the main issue is trying to fish out what they're actually trying to achieve for the designers. So I mean, one issue is that because I'm not in the firm, so I'm not working closely with them, so I don't really have a good sense of what they're going for and how they are trying to address the brief. That's one issue. And the other issue is that I can't fish it out, like what is it that they really want to do, because I mean, computation, I have to encode it in codes, right? So it has to be there needs to be more certain as compared to a design process where you sketch and then you react and then you move and then you slowly take a step forward, and as you take a step forward, you kind of detail your design better. But for computation, it's hard to do that. So that I have to ask, so what exactly do you want to do? How do I parameterize the model? What performance are you looking at? So like, depending on the project, you might be more interested in certain performances. How do you want to evaluate it, and so on. So like that, it's a huge task to encode that, especially in the early design process when everything is very fuzzy and everything is in flux. So, and then that kind of hit me that, oh, it's not just a technical obstacle. It's really about the difference between the design process and computational process. So that's something that is more fundamental and more that we really need to look into if we want to see these techniques scale up and be more widely used in the industry. So that's kind of my view on that. So that's the main obstacle. And I see the main opportunity is actually not architects using it, but actually clients and developers using this system. Because if you look at developers and clients, they have a very more narrow portfolio. For example, certain developers only they develop like hotels or offices. So you can set up a workflow that is kind of catered to let's say offices, and they can test out their brief. So once they have a brief, for example, they have a site, they work out how much they want to build. They can kind of parameterize that and and base it on existing design, right? So it's much lesser of a design, but rather an exploration of a brief. So it's more computation, it's less design. And then once they run this process and explore the brief, what they generate can be given to, let's say, the architects or the designers and say, so this is what a computer can generate, and this is roughly the performance boundary of what you can achieve at this site, and so on. As an architect or as a designer, I want you to design something better. Better in terms of looks, in aesthetic, and better also in terms of performance. And I would only kind of engage you more if you're able to do that and satisfy my brief. So it kind of helps clients or developers develop more well-defined brief for the designers and the architects. So I think that there's an opportunity there on the client and developer side, rather than trying to help the creative design process.
Oh, that's awesome. Yeah, I actually, when you explained that, I really thought, yeah, okay, yeah, that makes a lot of sense. So no, it's a good way of turning the perhaps or maybe a downside into a positive side. Yeah, it's a good idea.
Yeah.
Okay, so with that, I thank Dr. Chen and Darren Burrows for sharing and making time for this wonderful sharing session to the IBDC participants. And also, we actually open up this to anyone who actually wants to, join in. So it's great. So I think the video is going to be, I think Pong from BCA would somehow post the link in his computational space website as well. So it will be towards reach of many people then, right? So okay, I think I will close this session. Thank you once again, and maybe towards once we have received submissions, maybe we can share with you some of the things that the participants will have submitted sometime in September. Yeah, we would let you have a look at that as well. Right. Okay, thank you, Darren and Dr. Chen. And thanks all for attending. There'll be another webinar session on the 14th of June, so do keep a lookout at the IBDC 2021 website. All right, so the link will be posted there. So hope to see you all there as well. Thank you. Thanks.
Thanks everyone.
Bye-bye.
See you.
Bye. Okay, see you.
See
Bye.
ya. Bye.
Bye.